Obviously, we're delighted as the InstMC to host this joint technical meeting this evening on something which technology at its best, I guess, over the years. And obviously, I'm sure we're in for a good talk. I won't introduce John too much because on your poster it does actually say what John's background is. So, as I say, without further ado, to start off the evening, I can introduce you to John Farley, who I'm sure will give us a good presentation this evening.
Thank you. Well, good evening, everyone, and please may I have my thanks to turning up on a night like this. If I've been speaking down south, I'd have had about 8. Right? But I suppose they've made a different stuff down there. What I would like to talk about, basically, is 2 aeroplanes and what went on between them. The first aeroplane is the one that's in the top right-hand corner of that picture. Am I in your way there? Which is the P1127, and as you can see, it's hanging from the roof of the Science Museum in South Kensington, and the other one is on the bottom left-hand corner, which is the JSF. Now, there's 41 years of engineering development separates those 2 pictures. So I'd like to just take you through that period of time. Am I in anybody's way there? No? Fine. Well, as you can see then, the Hawker P1127, the prototype, which was registered XP831, it hovered in October 1960, so 44 years ago now. And it started what was destined to become the Harrier family of vertical and short takeoff and landing aeroplanes. And there, if you have a look, you will see the beast going about its business over a rather funny, I don't know if you can just see it at the back, there's a black line there, I'll talk about that later. That's a pit. But there you see this early aeroplane hovering back in October 1960. And after a very distinguished career, it finished up, retired to the Science Museum in South Kensington. And this is where they were taking it in through the wall. And there's a better picture of it inside. Now, as far as I'm concerned, people say, what a terrible end, to finish up in a science museum for an aeroplane. And I say, no, not at all. When it's done the sort of work that this aeroplane has done, to finish up in a museum as opposed to 10 feet down in a hole in the ground, is actually the accolade for the aeroplane, really. Now, in October 2001, just 41 years after 831 first flew, the Lockheed Martin X-35 won the Joint Strike Fighter competition for a stealthy, supersonic, short takeoff and vertical landing aeroplane. And there you see it going about its business. So then, this is the story of the 41 years of VSTOL flight development, and in particular, folks, the names of 8 engineers who I believe were the key people who made the decisions that made this whole thing happen. All of the decisions of these 8 men were taken before 1960. In 1956, one man had an idea. His idea was for vectored thrust. He was a French engineer, but we won't hold that against him, will we? His name was Michel Vibo, and he suggested using rotating nozzles to vector thrust all those years ago, back in 1956. He took his idea to Marcel Dassault, who, as many people in this room will know, is Mr. French Aerospace. Second name. Marcel Dassault wasn't interested. He said, oh, that'll never work. A bit like, I suppose, you and I hearing the first demo tape of the Beatles and saying you never sell that stuff. I mean, he got it wrong, didn't he? I mean, he got it badly wrong. And if he hadn't, then it might well all have happened in France. So what was Vibo to do? He went to United States Air Force Colonel Johnny Driscoll, who was in a Paris office of an organisation called the NATO Mutual Weapons Development Office. Remember, this is 1956, just after the Second World War, and the United States were trying to pull together this new thing, NATO, and trying to get some commonality into the armed services equipment. And it was at this stage that the United Kingdom became involved, because when Vibo went to Johnny Driscoll and asked him what he thought, and also Driscoll's successor, Bill Chapman, because Driscoll was a serving officer and like all serving officers, they come and go in post. Both of them agreed that apparently it was a good idea, but they were not qualified to really pass judgment. But they knew somebody who was, and the somebody who was Stanley Hooker. Stanley Hooker was the chief engineer of the Bristol Aero Engine Company at the time, and both Driscoll and Chapman were working with Hooker on other projects at that time. That was how the United Kingdom became involved. Hooker agreed to look at Vibo's design. So we're now talking of a serious engineer having a look at the thing that Vibo called a gyropter. That's what it looked like, folks. So what Vibo did was, if I'm going to look at the screen, perhaps I better turn that on. What Vibo did was to take a good engine of the day, a Bristol Orion turboprop. I mean, it was as good as they come in that period of time. 8,000 shaft horsepower, and instead of driving a propeller off it, which is of course what the engine was designed to do, he had this system of shafts, gearboxes, and centrifugal blowers, and with which he was, I mean, just like huge hairdryers, with which he was going to produce these 4 jet effluxes. And he could rotate these things, and so he called them, I think, volutes. The idea was obvious, you know, here's vector thrust, this is how we can push this aeroplane around by itself. Right, Stanley Hooker's view on this then. He was extremely unhappy with the mechanical complexity used by Vibo, but he did like that thrust vectoring notion. And like all good guys, senior guys, he had a good young man. And so he gave the job of coming up with a better way of using this idea to one of his young engine designers, a chap called Gordon Lewis. So Lewis and Vibo worked together on the engine. Gordon Lewis's main input was that he felt that the airflow from a turbine-driven fan, as opposed to those 4 centrifugal blowers, could be vectored directly. And he and Vibo worked together, and they came out with a patent for such an engine in January 1957. So here is their first engine. They ran this one, folks, and it was cobbled together from existing parts of existing engines. It was, if you like, just a demonstrator of the idea. The front part, because the air comes in at this end, the front part was the first 3 stages of an Olympus low-pressure compressor. Now, the Olympus was the engine that was going into the Vulcan, it was the engine that was going to go into the TSR-2, and it was the engine eventually that powered Concorde. So they took just the first 3 stages of this Olympus low-pressure compressor. And then they took the Orpheus, an engine gas generator, which is the complete turbojet part of it, and they put an extra turbine in, and they drove these stages at the front with a shaft. Now the interesting thing is that the air that was going to the gas generator went through a circular intake, which was, it wasn't just a big hole, it was a circular arc. And the air for the fan went in through the centre, and so it was quite separate. In other words, the air that went through the fan never went near the gas generator. So let's imagine you're the air coming in the fan at the front, you get compressed, and then you come straight out of these front nozzles, which were vectoring, could be swiveled. Now, I think you can see that that was merely just an attempt at seeing whether they could get such an engine running with some swivelling nozzles on it. Now, at this stage, Hawker Aircraft came into the business, because at the same time in history, Hawker's legendary fighter designer, Sidney Cam, was also considering vertical and short takeoff and landing. But Cam did not like the multiple lift engines that Rolls-Royce were providing for the short SC-1 research aircraft. Now we go slightly sideways now, folks, and this is the short SC-1 sitting on something that I've described as the Bedford Pit. Well, first of all, the aeroplane has got 4 vertically mounted jet engines with their air intakes on the top and the exhaust at the bottom. and another one out the back here, mounted horizontally. This aeroplane, the short SC-1, started flying around 1959. Now, what's this pit? Well, if you think about it, if you're going to try and do something different, like take a jet aeroplane and point the jet down at the ground and just blow yourself up in the air, when that jet hits the ground, woof, it spreads out everywhere, it's hot, it's very high energy. Some of this is going to bounce off the ground and hit the bottom of the aeroplane. You are really sitting there when you try and do a vertical takeoff in those circumstances in your own mess of rubbish, you know. I mean, it's terribly turbulent and buffeting and so on. And it's not really the way to start to find out how to do things carefully. But if, on the other hand, you dug a great big hole in the ground and you covered the top of the hole over with a grating, and then you made some arrangements for the air that blows from the engines down through the grating without rebounding to duct it away somewhere, out through a pipe or behind the aeroplane, then of course you can do what we call a free air vertical takeoff. It's just as if the aeroplane wasn't being affected by the ground plane. And this pit was used at Dunsfold and was that sort of black mark on the ground. And later, when we look at the JSF doing a movie of its doing its first hovers, it was flying over a pit to start with. Now, I know as soon as you've got the aeroplane sorted, you're going to have to work it from the solid. Otherwise, you're going to have to ask the Air Forces and Navies of the world to go around with pits or some special launching site. But it's a case of learning to walk under reasonably calm conditions before you say, okay, we know what to do now. We can just break free from the ground and the solid. Okay, so that's the Bedford pit. Now, this particular aeroplane was... What are these noises off? Is it that, perhaps? Maybe. Right. I'll just use it when I have to, all right? Because if it doesn't annoy you, it'll annoy me. This aeroplane was at Bedford in 1964. And I did the Empire Test Pilot School in 1963, and I was posted to Bedford on the aerodynamics research flight in December 63. This aeroplane was already at Bedford then, and the boffins were flying it from this pit. And the first serious job that I got out of ETPS was I was asked by the boffins to go down to Dunsfold, which was Hawker's aerodrome, just south of Guildford, and collect from there the prototype P1127, which we mentioned earlier, the one that's hanging, the very one that is hanging from the ceiling in the Science Museum. And I was asked to compare that vectored thrust way of doing things with this, which is called the lift plus cruise approach. Now, I mean, as far as I was concerned, best job in the United Kingdom, you know, and I couldn't understand why I got the job. There were 4 pilots at Bedford. I was the most junior one, only just arrived. The sort of job you expect the boss to get. And it was only when I talked to the boffins later, I didn't bother them with the question before I'd gone and got it and done the thing and so on. I said, well, why did I get the job? And they said, well, it was just a case of money, wasn't it? Now, what they were talking about was that the aeroplane that I collected from Dunsfold, XP831, had an engine in it that had a 1-hour life. Right? Now, that's 1 hour when the nozzles were deflected. 25 hours running was allowed when the nozzles were aft. But of course, nobody was really interested in flying around conventionally. We had a reasonable idea how to do that. But this vertical thing. So, well, what happened after you'd had an hour of nozzle down operation? They had to take the engine out, send it back to Bristol, where it was manufactured, do a complete strip overhaul, and on every occasion we sent it back, there was at least 1 blade missing from the hot end. Stator, not rotor, because it would have shaken itself to bits, of course, but just the stator. So they had it lifed about right, folks. And the reason that it was such a short life in those days was that it was quite difficult to get that much thrust, or the thrust slightly greater than the weight of the aeroplane, out of one small engine. So the thing had to be thrashed pretty hard. And I mean, in round numbers, we were looking at sort of 11,000 pounds of thrust on an aeroplane that weighed about 10,300 pounds, and then you had to put a pilot in it, then you had to put a bit of fuel in it, so there wasn't a lot to spare. However, I've digressed a bit there. There's a picture of the SC-1 Airborne, and you can see perhaps more clearly, well, here's the exhaust pipes of the 4 vertically mounted engines, and of course the one at the back. Now, this aeroplane was an interesting aeroplane to fly because there was no automation in those days. It's got 5 engines. It's a single-seater, so you're flying a sort of 5-engine bomber by yourself. So there's quite a lot involved in operating the aeroplane. It was very short of fuel, and once you started the 4 lift engines, you weren't going to have them running very long, a minute or 3 sort of thing. So when you were coming into land, and before doing a vertical landing, you set about starting these 4 engines at 200 or 300 feet on the approach, where most people, you know, are thinking, well, I think I've got this about right now, let's think about the landing. You were quite busy. But on the other hand, it had quite delightful handling characteristics. It was quite easy to keep the wings level and to keep the aeroplane pointing the way you wanted it to go, that sort of thing. Control your height and speed. The P1127 wasn't such a nice aeroplane from a handling point of view, because the intakes were right in front of the centre of gravity and it wanted to turn around and fly backwards. And so to keep it going the way you were facing, you had to use your feet fairly extensively. But of course it was such a simple aeroplane to operate. So that was the essential difference between those 2 concepts. The Jean SC-1 came out of a thing that Rolls-Royce started flying in 1953. It's the Rolls-Royce thrust measuring rig, or flying bedstead, as probably most people will have heard of it. And that was merely an experimental rig to just prove that you could point jet engines down to the ground and hover the thing. Okay, Sidney Cam's input then, going back to how this all happened. Because of the complexity of multiple lift engines that I've just been talking about, he wrote to Hooker, the man who had done this engine, asking Hooker if he had any alternative ideas. And Hooker confirmed back to Cam the details of the Louis Vivo engine. But as it happened, it took him about 2 weeks to answer Cam's letter, and Cam had, in the meantime, heard about it all from Hawker's agent in Paris, who was obviously two-timing the 2 companies working for both of them. Sort of. Anyhow, they got to hear about it. Cam passed this brochure into his project office, the place where all his bright young men were. He did not give it to anybody in particular, he just threw it on the table and left it there. And one of his young engineers, Ralph Hooper, the 8th name, he decided to try and draw an aircraft round this engine. Well, you remember the engine, that's the one I showed you earlier. You can see what Ralph's problem was, the rear exhaust. It didn't swivel. So Ralph's first try had a nose intake in June 57. He propped this thing up on a very sort of ungainly undercarriage to try and get some sort of lift component out of the unvectored bit of the engine, as well as, of course, having the front bits facing forward slightly to try and stop this thing moving. A totally unsatisfactory thing. And a few days later, he had another one with some side intakes which were better, a bit more space for the cockpit, bit more room for equipment and so on. But he didn't think much of this at all. He did not really think this thing could be made to hover or vertically take off. And then coming into work one Thursday morning, he had this brainwave. Why don't we split the rear exhaust? And if you talk to Ralph and say, oh, you know, how do you get an idea like that? He'll say, you don't know. I mean, ideas just come. Once you've had it, of course, you and everybody else think, oh, why didn't somebody else think of that before? But Ralph had worked on an airplane called the Seahawk, which, as some of you may know, was a single-engined airplane, and they bifurcated or split the rear nozzle, and had it come out just behind the trailing edge of the wing, rather than a jet pipe all the way down through the rest of the fuselage. So that was probably what triggered it in Ralph's mind. But of course, as soon as he came up
went back to to Bristol as it was then, and said, look, how about we put 2 more nozzles on the back? Then we had a V-style engine at last, didn't we? And this was the first Pegasus. Now, compared to that original demonstrator, the BS-53, we now have a conventional intake at the front, one intake feeding the whole of the engine. Now, if you are the air, and the gas turbine experts in the room will have to forgive me if I just explain that if you're the air and you come in the front of this thing, you meet these blades that are going around very rapidly, or rotating very rapidly, and they get hold of you and they squeeze you up and they compress you. And by the time you've passed through the fan stages, you've got to here in the engine. You have a decision to make. Should you nip on out through the front nozzle, like that? Or should you go on down through that route? Well, the air that comes out of the front nozzles is said, quite reasonably, to bypass the engine. It's the bypass air. Now, with bypass engines, there is a lot of interest about the ratio between the air that comes out the back and the air that comes out the front. The bypass ratio of this thing is 1.3 to 1. So it doesn't matter what units you use, just over half is coming out the front compared to coming out the back. Okay, well, I didn't say that properly, did I? Just over half the air comes out of the front, and just under half the air comes out of the back. So there's a bit more coming out the front than the back. The most modern example of a bypass engine is the sort of thing we see on modern airliners. And the bypass ratios there are as high as 7. In other words, only 1/7 of the air is coming out of the back of these engines. However, you are the air, you have decided you're coming out the front here. And your front, you are cold air, you've had no fuel burned in you. Okay, you're warm because you've been compressed with the bicycle pump effect, but you've not had any fuel burned in you. So the paint's not going to come off these nozzles, for example. But the air that goes on through meets a whole lot more rotating blades. These are much smaller, they're meaner, they're sharper, they're going around an awful lot faster, and they get hold of you, and they squeeze you up, and they really compress you. Until, by the time you get to here, look how small that passage is that the air is going through. Now there's a fair amount of old money in the room, so I'll start by saying it's £135 per square inch when it comes out the back of this HP compressor. Nearly 10 atmospheres for those who've got a bit of life in front of them. For somebody who's only interested in motor cars, then it must be about 4 or 5 times the pressure that we put in our motor car tyres. So this is pretty excited air, and when it's released it wants to do something. And it's released at this point to go through this part of the engine, which is the combustion chambers. And it's in here that the paraffin is burnt continuously, which of course heats the air, expands the air, and it goes rushing out the back. But, and it's quite a big but, there's something else in the way, and the something else is a few more rows of blades. Now these aren't going round, these have got to be blown round. These are, if you like, windmills, these are turbines. These are extracting energy out of this air. And of course the reason we've got to have something to extract some energy out is that you've got to have something to drive the shaft that turns this lock in the first place. But you're still left with a fairly extensive residual jet. Okay, Ralph Hooper's definitive P1127 could then be drawn. And this is the 3-view drawing of the aeroplane that is hanging from the Science Museum, the one that they told me to go and collect from Dunsfold. You know roughly how the engine is installed now because we've looked at the 3-view and you've seen the big engine. It's quite a big engine in a fairly small aeroplane. You know how the gas flows go, so we won't bore you with those again. Now, how do we control this thing? Well, on the left-hand side there, the big fat lever is the throttle. This whole assembly, this thing that is on the screen now, if you sit in the aeroplane, where your left hand just naturally falls, that's where this piece of kit is. So you push the throttle forward, the engine goes faster, you pull it back, the engine goes slower, every engine has one. But the nozzle lever, the thinner lever, push it forward and the aeroplane goes faster. Pull it back and the aeroplane goes slower. Because that nozzle lever is controlling a thing called an air motor. This is the system that rotates the nozzles, and it's not manually operated by your muscles when you pull the lever. It's like power control, power steering in a motor car. And it's called an air motor because its motive power is that 135 psi 10 bar stuff tapped off the back of the HP compressor. So when you move the lever, you're telling this big green air motor to spin the prop shaft that goes forwards and the prop shaft that goes back across the rear axle and the front axle and so on, a bit like a four-wheel drive motor car. I know the wheels aren't spinning, but they are rotating, and that way you set the nozzles. Now this may look extremely Heath Robinson. The final drive is chain and sprocket. Now I'm sure quite a few of you will realise why this is such a basic mechanical system. And it's because it must never go wrong. You do not move these nozzles independently of each other. When you move that lever in the cockpit, they all four move together. In your head, if you're going to go and fly the airplane and you're thinking about it, you can think of just tilting the whole engine. You don't have to think of it. The engine is being split into 4 bits. It doesn't matter. It's immaterial. You're taking the thrust of the engine, you're pointing it downwards or you're pointing it backwards. If one nozzle pointed in a different direction to the others, you would not be able to control the aeroplane. That is why this is such a simple, basic system. I mean, all those years ago when it was designed, and it's never broken, so I think that's pretty good. Now, when an ordinary aeroplane is flying along, of course, just like an ordinary boat going through the water, and you take in your boat, you move the rudder around, you can steer your boat. But moving the rudder around when it's in harbour doesn't do much good. And moving the things that you steer an airplane with, the ailerons, the rudder and the tailplane, around doesn't do you any good if there's no air going over them. So you've got to have a reaction control system if you're going to try and hover. And again, this is just a big pipe, goes to the nose and the tail and the wingtips. It's full of this same stuff that comes out the back of the HP compressor, 135 psi. And it goes to the extremities of the aeroplane. And at each extremity there is a shutter, so the stuff can't get out. Now, I said that when you flew your aeroplane normally, you waved these ailerons, which are the hinge surfaces on the wings. You wave the tailplane, which is the bit at the back, and you wave the vertical rudder. That is what you do in a Harrier. That is what you do in the hover. And the fact that those surfaces, which are controlled by your control column and your rudder bar, are waving about just as they always do because you're just in another aeroplane, that's not going to make it manoeuvre, but that's all you actually do. You wave those around. But there is a small mechanical link connecting the shutter to its appropriate control. Literally just a couple of links in a bell crank. And so when you move the normal surfaces that you are used to moving as pilots, in just the same way as you would if the thing was going along at 300 miles an hour, you actually open a valve and the air squirts out. So if you did a vertical takeoff and the right wing dropped a bit, for whatever reason, you knew as a pilot you just have to move the stick over to the left, and to put the aileron down, and it would allow the air to squirt out underneath here and blow the wingtip up. So the magic of it all is, from a pilot's point of view, you need to know nothing. You have nothing extra to move in the cockpit at all. Really, really neat, I think. But you look particularly unimpressed, but never mind. Okay, now let's jump ahead. You've got some rough idea of how this thing was put together. Bill Bedford tried to fly it, tried to hover it. There's the grid. You can recognise the grid now. At Dunsfold in October 1960. And straight away, a problem was born. You can see that this thing is tilted over at an angle. It's got this funny undercarriage and this lateral freedom, even after some temporary extensions have been added. Now, this undercarriage, it took 8 years to sort it out. 8 years. And it's worth spending perhaps a couple of minutes in discussing these issues. Now this picture shows the undercarriage layout. It is not the thing that we're more used to, which is a tricycle undercarriage, where you have a nose wheel and then a couple of legs somewhere out the back of the aeroplane, and you wouldn't have these little kiddie wheels. You couldn't have a tricycle with this thing because the main wheels would have been right in the efflux of the hot gases and so on. And there were other difficulties in getting the structure strong enough at that point there. So Ralph said, all right, we'll have to have a bicycle. Now with a bicycle undercarriage, you need to make arrangements so that when the aeroplane lands, the main wheels hit the ground first. Now when your airliner lands, the main wheels, the ones at the back, should hit the ground first. And the nose wheel is then gently lowered on. The undercarriage is not designed for you to arrive on your nose wheel or even on all 3 points together. If it were designed to be strong enough to behave like that, then the whole thing would be a lot heavier. So with a bicycle undercarriage, you still have to meet those sort of rules and say, well, which leg is it we're going to use to absorb all the impact? And the answer is the main leg. So this has got the necessary strength and the necessary compression and oleos and dampers and so on in it, such that when this 8-ton thing comes drifting down and hits the ground, and these main wheels hit first, that main leg absorbs the impact. And of course, in absorbing the impact, it squashes up. There's a lot of stored energy in there now, and as soon as the momentum of the aeroplane has been killed, and all you've got is the weight of the aeroplane left, then of course the leg comes back out again, and this thing gets floppy. Well, it's no good trying to do a vertical takeoff when you're tilted over like that, because you'll just go juddering across the surface, long before the thrust gets big enough to exceed your weight. So there's real problems. And it wasn't, and as I said, for 8 years we struggled with these aeroplanes having terrible ground handling. And then Ralph, was the same bloke again, Ralph Hooper, he came up with this idea of a self-shortening leg, which was perfection again. Another brilliantly simple notion. The main undercarriage leg, the damping and so on, is done with basically a hydraulic system. It's got some nitrogen charging in there, but it's essentially a lot of oil. And when that stuff is compressed, or when it is being forced, because you can't compress oil, when it's being forced up through the appropriate passages and is absorbing this impact, instead of sitting against the accumulator at the top, which is full of air and a piston, and then pushes it back down again, it's siphoned off into an accumulator. So you get no rebound. It's done all the work in absorbing the energy of impact, but it doesn't retain any compressive forces inside it. Goes off into an accumulator. When you next take off, whatever that might be, the main leg just slides out again under its own weight, and it sucks the oil back in, and it's all ready for another sequence of action. You know? So, I mean, brilliantly simple concept. Weighed virtually nothing, and I mean, it was, with that, you land on your main wheels, then the airplane just rests on all four, flat as a pancake, and it behaves beautifully on the ground as a result. Okay, now I'm going to speed up a bit. The Harrier GR Mark I went into service with the Royal Air Force in 1969. So we've moved on now. We've finished with this P1127 thing, which was the starting point. I've only mentioned one of the problems, which was the undercarriage, but now we're looking at the GR1. Now, when this thing went into service with the RAF, it was the very first RAF aeroplane fitted with some advanced kit. It was the first one ever to have a head-up display. It was the first one to have an inertial navigation system, and it was the first one to have a moving map display. Now, I know a lot of people probably think that the Harrier is a bit of a sort of gimmicky thing, and it was just designed to improve the quality of air shows, but it's not that at all. It has always been right at the leading edge, not only of how to take off and land, but the sort of equipment it had got to go and do its operational role. A few years after the thing went into service, I'm talking 74, 75 time now, 5 or 6 years after, we had all the airplanes back, 3 or 4 at a time from the Royal Air Force, and we fitted into the nose a thing called a laser. It was actually a thing called an LRMTS, Laser Rangefinder and Mark Target Seeker. Now, time was when I used to have to explain to people the value of using a laser in terms of aiming weapons, and it isn't necessary anymore. Good. This thing, this equipment, again, it was the first RAF aeroplane to have this kit. It transformed the weapon accuracy of the Harrier force. The United States Marine Corps started flying the airplane in 1971, and their reason for being is amphibious assault. And so, to go about their business, they would put a lot of their soldiers, or grunts as they call them, in a boat, and they drive the boat to about 50 miles from the beach that they wanted to land on. They get them up on the deck and put them into the helicopters, because this is not an aircraft carrier, folks. This has no catapults, no arrestor gear, just a flat top troop ship, if you like. And they put them into the choppers, and they take off and they go yugga-dugga-dug to the beach. Well, they did this all through the Second World War when they didn't have helicopters. And they did it through all the islands in the Pacific. And in those days, they had to drive the troop ship or the landing ship to within perhaps a couple of miles of the beach, and then they all got down scrambling nets, and they got into little tiny landing craft, and they buzzed off towards the beach. And some of you are old enough to remember that John Wayne was waving out the front of each one, wasn't he? But that's not the way they do it now. They do it with helicopters. But in the mid-40s, there were 1 or 2 landings that they did where the promised air support, which was to come from an ordinary aircraft carrier and protect their troops as they tried to get the beachhead sorted out, didn't arrive, and that chap's got massacred. Now, in 1970, the generals running the Marine Corps were some of the survivors of those awful landings. And they had been saying all along, we want our own aeroplanes that we can fly from our own small ships. We want VSTOL. So they came and bought it from us. Don't listen to anybody who says that we sold it. We didn't send salesmen over to the United States at all. I mean, we had to go over and explain the thing, but I mean, they made the first approach. And now, something that I haven't mentioned is that, and it's pretty obvious to an audience like your good selves, that if you want to take off vertically, you better have a bit more thrust than you got weight. Because if you try and do a vertical takeoff when your airplane is heavier than your thrust, then you can pull that nozzle lever back and point the nozzles down at the ground. You can open the throttle, and it'll hoot and roar, and it'll shake, but it won't go anywhere. Well, what does that mean? Does that mean that in those circumstances, well, things just no good? Well, let's look at some of the numbers. When it first went into service with the Marine Corps, and the Royal Air Force for that matter, it weighed about 12,000 pounds. It had an engine of about 19,000 pounds of thrust. These are round numbers. So it had a vertical payload of about 6.5 if you wanted a bit of a go. Well, 5,000 pounds of that 6.5 would be used up with filling up the fuel tanks, and so you could only put a couple of 750-pound bombs on. If you want to take off with 4 1,000-pounders or something, then you'd be quite poorly placed. You'd be 2 or 3 tons too heavy. So what do you do? Well, the answer is you do a short takeoff. You say, all right, how much too heavy? Okay, 3,000 pounds too heavy, right. Okay, now you've got a little chart and it says, how fast does the wing have to go to make 3,000 pounds of lift? Oh, I see, 70 knots. All right, fine. So now you just run along the ground with your nozzles aft until you get 70 knots, which you get very quickly. Bang the nozzles down and you jump into the sky on a short takeoff, as it is called. Mixture of wing lift and jet lift. Now, if you want to do this from your ship, say you're at this bloke here, you see, and you're too heavy to take off vertically. Well, you ask this bloke here to move his helicopter, all right, and then off you go. And when you get to the end of the deck, and it's very obvious when you get to the end, just pull the nozzle lever back and you'll fly away. Now, that's fine on a day like this. But you know, the sea is sometimes very rough. And when the sea is very rough, we all know that steamers, you know, they go off in the water, don't they? And they go up and down like this. And with your luck and my luck, by about Wednesday afternoon, we get to the end of the deck just as it was pointing downhill. And so that's no way to start the trip at all. And at night, quite seriously, and at night you can't even see that the deck's pointing down, because there's no lights out there in the middle of the ocean at night. Really dark. And well, the answer to all of this was we had to make the aeroplane lighter, in terms of couldn't put so much fuel and weapons on it if you're doing a short takeoff when the sea was very rough, just in case you got it wrong. Now you might say, well, can't you just sort of look out the window and judge how the ship is going up and down, and okay, and if you go off when it's doing that, by the time you get to the end it'll be doing that. Well, yes, you can 9 times out of 10, but the waves are not totally regular, and ships have this unfortunate habit of going, you know, they go like this a few times, and then they go, off, and they take the next wave off while they're still down, and then it comes up. So it's called a dwell if you're in the Navy, and ships do dwell occasionally. And of course, you know, that means the whole thing is bad news, and you've lost a lot of performance. And so Doug Taylor, a young lieutenant commander in the Royal Navy, he came up with this idea of putting a curved ramp on the front of the steamer, such that the exit angle of the ramp was always greater than any bow-down tendency, and the ski jump was born. Now, we extended this ski jump beyond just coping with ship motion, because we found it was such a beautiful way to get airborne. There was a trial ramp built at Bedford, and it was adjustable in angle. We started at 6 and we made our way in stages up to 20. And it was brilliant, really magnificent way, ever so easy to get this very heavy airplane airborne from a very short distance. And the ramp, all by itself, delivers you into the sky, going upwards and in a climbing attitude. I mean, I raved about this after I did the first few ski jumps, and the boffins clearly thought I was way OTT on this. And they thought I must have got a thing with Doug Taylor or whatever, you know. And in order to convince them, because this was an instrumented aeroplane, I did one ski jump without touching the stick for 35 seconds. That's a very long time. And when I went into the debrief and they got the instrumentation traces out, they said, oh, we got an instrumentation problem. The stick and the aileron went straight line. It's called a dropout in the, well, we got some instrumentation people in. It's called a dropout in the trade. I said, no, it wasn't a dropout. I wasn't holding the stick. And they had to agree then that if you've got nothing to do, you can't have a much lower workload than that. Okay, so the ski jump was great. And that's a different shot of the thing at Bedford. Come 1978, we had this new thing called a Sea Harrier, and it first flew in August, and I was taking it to the Farnborough Air Show in September, and they had an argosy going up the channel, and some photographers in it were waving their arms, and you know, and I was taking some pictures of me. Rather poor video, but there was a decent still photographer there, who manoeuvred me into a position where I think he felt it had only got one wing. I mean, I never did understand why he wanted that shot, but there we are. Having got the aeroplane to Farnborough, we then ran it up the ski jump. So this is the first time the Sea Harrier had been seen at Farnborough, and it was, well, the public had seen the Sea Harrier. It was only a few weeks old. Running it up twice there because it's only a short clip. And the public had never seen the ski jump either. And you can see it was just a temporary thing made out of medium girder bridge, the stuff the army uses to get tanks across ravines and rivers and so on. Okay, so we've got through to 1978. Now, I want to talk about a thing called the Harrier 2. Now, this thing is actually a family of aeroplanes. All the Harriers to date have belonged to the Harrier 1 family, Roman 1. And the difference between a Harrier 1 and 2 can be seen here. The Marines said that for their next aeroplane, remember they'd had the aircraft now 8 or 9 years, the next aeroplane they wanted another Harrier that would go twice as far or another Harrier that would carry twice as much and go the same distance. Double the payload radius of action was how they described it. Well, this, and there was no money for a new engine. So this clearly made people say, well, we've got to do something with the wing. We've got to get a lot more lift. They also wanted to get more off from a vertical takeoff, and so the blue bits here were designed by McDonnell Douglas and fitted to one of the, in fact to two of the American Marine Corps aeroplanes. And these airplanes were going to, the blue bits are the changes from the AV-8A as they called their thing. Big new wing is obvious. There's some changes to the intake to make the engine breathe better and so get more thrust from the same engine. Some changes to the nozzle likewise. And also a rather clever thing underneath the fuselage here, which the Brits had actually developed, but we'd never done it properly. We'd only done a small version of it. When you do your vertical takeoff, those four jets, you know, when they hit the ground, whoosh, they spread out radially in all directions. Splash. Just like holding a hose pipe of water in front of you, you know, some of it's going to splash back towards you and your feet are going to get wet. Now, some of this air is going that way, some's going away, but some of it is splashing forwards and towards the centre of the engine from the back right-hand nozzle, and some is going backwards and towards the centre from the front left-hand one, and so on. So when this stuff that is going diametrically towards the centre meets its opposite number, it just curves up and presses on the bottom of the aeroplane. Well, if you contain that fountain effect, as it is termed, this is beneficial ground effect, of course. If you contain that under a big sort of three-sided open box, then you can get a lot more weight off. And we demonstrated 1,400 pounds more vertical takeoff payload, and that's net, not gross, just for having these big strakes underneath. Now, I went over to the States in 1979 to fly this blue stuff. We were flying it for about 18 months to see if it did the job properly. While we were doing that, the boffins and designers were doing the red bits, which were considered to be not really high-risk stuff, and if the new wing worked well, then we could have put the red bits and the blue bits together, and we'd have a Harrier 2. Here's the comparison of the two wings. The yellow wing is this Harrier 2. Look how much thicker it is. Look how much fuel you're going to get in that compared to this. So this is the GR1, the GR3, the Sea Harrier, and so on. Much bigger flaps, huge flaps, so that we could get very much more weight off from the same short distance. So you've got to have big flaps. The flaps are so big now that you couldn't put them down when the nozzles are aft, or they'd just blow off, and so they became linked with the nozzles. The little wheel moved in to halfway along, not for any structural reason, but because the Marines wanted to fly from narrower roads, and that's the simple reason. You can't have your kiddie wheel in the ditch. You don't mind having your wingtip over the ditch, but you've got to have the wheel on. So, okay. Now, we're up to date now. This is the Sea Harrier FA2. This is the aeroplane that is currently in service with the Royal Navy. It's not the aeroplane that went down the Falklands. That was the FRS Mark 1. This is the Sea Harrier FA Mark 2. Now, the aeroplane that went down to the Falklands, its only air-to-air armament was a thing called Sidewinder. Well, apart from a 30mm cannon, but Sidewinder was the main weapon. A 1 to 2 mile range heat-seeking missile, which you fired at other aeroplanes. Now, tremendous constraints on this. The pilot had to see the enemy aeroplane before he could fire the Sidewinder. The Sidewinder had to see the enemy's heat before you fired it. And you knew when it had locked on because there was a growl over the intercom. So if you fired it when it wasn't locked on, or if you fired it beyond about 2 miles, it wasn't going to guide. So not much more than a sort of long-range accurate gun. But this thing, this Sea Harrier FA2, has got this thing called an AMRAAM, an Advanced Medium Range Air-to-Air Missile. This is a sort of 30-mile piece of kit. This can be fired at something you've never seen. It can be fired at a target that's in cloud. It can be fired at a target in the night. So how does all this happen? Well, your Sea Harrier knows where it is. It's got a very good modern inertial navigation system and so on. And so it knows either on a grid or lat and long basis where it is. And it is continually telling the 4 AMRAAM missiles that it has on its pylons where they are. Your aeroplane also knows by its radar where the enemy is. Your aeroplane may also know where the enemy is by being told by some other command and control airplane through the data link. And so your aircraft now has an enemy position. It's got its own position. And so it can put up on the radar scope, it can, I hate the word prioritise, it can choose the 4 worst threats to the fleet, put circles around them, and all you have to do is to press the accept button. And 4 AMRAAMs will then go off at these things. Now, when the AMRAAM goes off, it knows the position it started, it knows the position the enemy's at, and it's got its own inertial system, and off it goes. Now, of course, the enemy can manoeuvre on the way. So when it's about halfway to the enemy's position, it's going pretty quickly. When it's about halfway to the enemy position, it turns on its own radar and homes actively the last bit of the way. I talked to the lad who fired the first 4 of these against drones in the United States, Rod Fredrickson, and Dunsfold test pilot. When he came back from this, I knew that Rod was a former Falklands War veteran, and he shot down several aeroplanes with Sidewinder. And I said to Rod, what do you think about this then, this AMRAAM and just capture and accept? And he said, takes all the fun out of it. Well, because he wasn't being entirely serious, was he? Because, you know, it's not a funny business going down shooting other people. But we must do, we, the boffins, we, everybody, must do what we can to make sure that if we send our people off to fight a war, then they have got the best possible kit. And clearly this is a very good kit. Now, the Royal Air Force flies Harriers. They fly Harrier 2s. That thing is a Harrier 1. That has got the thin wing. And by the way, the thin wing aeroplane is nearly 100 knots faster than the thick wing aeroplane. But this is a fighter. This one's a bomber. This thing has GR7. As the slide says, it's operational in the night low-level role using a forward-looking infrared head-up display and night vision goggles. What on earth does all that mean? Well, it means that the guys and girls are flying around at 250 feet in the middle of the night, looking out of the window and low-flying like somebody would do in the middle of an ordinary air show. In other words, just flying visually, not using instruments, just looking out of the window, on totally synthetic vision aids. It's completely black out there. Now, I think that's just amazing. And they had tremendous success in the Second Gulf War. In fact, I was talking to Stuart Ather, who was the CO of 3 Squadron after they came back from the Falklands, from the Gulf. And he wouldn't tell me all the details of what they were been up to because they had a particularly classified mission. Their unit, this is number 3 Squadron in the RAF, were the only unit in the coalition forces who had no press with them, ever. I don't know where they were based, I've no idea. It might have been somewhere inside Iraq, it might have been, I don't know where it was. They were given 6 months special training for this mission. And their job was to make sure that the Iraqis fired no missiles out of Iraq into other countries. So if you like, a scud hunt. And on the first night of the war, Stuart Ather did 8 hours 40 minutes in one sortie with his GR7 on this job. 5 flight refuelings during the sortie, all low level, all at night. The best pilot that 3 Squadron had, the most successful, and they got a string of DFCs, DSOs and so on amongst them, was the young lady. And now it doesn't surprise me that, that the young ladies are better at the job than the blokes. because, I mean, when it comes down to it, I think a woman who is pushed is more ruthless and vicious than any of us, basically. Perhaps I've been unlucky, but I mean, seriously, they should fight the wars, shouldn't they? You know, I mean, this is dodgy ground. Okay, now I want to talk about the future. The VARC Harrier, Vector Thrust Advanced Aircraft Control, or something like that. This is a program that has been running since 1971, and it reached its climax a couple of years ago. I went to the very first meeting on this program in 1971, and the program was designed to make the Harrier easier to fly, to remove the need for special training, special skill, or anything like that at all. And I listened to what the boffins wanted to do, and I came away from that meeting. It was at Farnborough, and I was at Dunsford at the time, and I thought, that's really wonderful. It'll take about 18 months to sort that out. Well, it took 32 years, and it's been brilliant. Now, what we're talking about is handing over control of the aeroplane to a computer. The computer controls are in the back cockpit. This is the experimental cockpit. This is a standard Harrier two-seater front cockpit with all mechanical controls and so on. With this piece of kit now, they've taken a young chap who just got his PPL, in other words, he's got 40 or 50 hours in some Cessna or something, put him in the back cockpit and said, okay, we want you to do a vertical takeoff, accelerate away, go around the circuit, come back, decelerate, do a vertical landing. You give me a brief. Yeah? If you want to go up, pull a stick back. If you want to go down, push it forward. It's a concept you're probably familiar with. But you can do it independent of speed. If you want to go left, move it to the left. If you want to go right, move it to the right. That's what you've got to do. If you want to go faster, then push that lever forward. It's called the throttle, not a lever. If you want to go slower, pull it back, the engine. In fact, when we were developing this, I wanted to get rid of the throttle as well. I preferred, because we tried various ways of doing this, I preferred it with the switch on the top of the stick. Hold the switch forward to go faster, hold the switch back to go slower. Then you had nothing to do with your left hand. You could use it for other jobs associated with the operational equipment of the airplane rather than flying it. But that seemed to be one step too far for the other pilots, and so they have got this thing that looks like a throttle. Now, so, you get in the back cockpit of this thing. The safety pilot is called in the front because you've got to have a safety pilot. There's only one of these things in the back. And it's not multiplex as it will be in service. You want to go up. Okay, fine. We'll pull a stick back. So you sit in dispersal and you pull a stick back. The computer says, oh dear, this bloke wants to go up. Doesn't he realise we're just sitting in dispersal, we're not going anywhere? So it puts the nozzles down, it opens the throttles, and up the airplane goes on a vertical takeoff. As you see the ground falling away, and you're about 20 feet up, you let go, you go, ah! And the stick goes into the centre. And the computer says, oh, right, okay, he doesn't want to go up, doesn't want to go down, doesn't want to go left, doesn't go... It just sits there in a steady hover. If you're a smart-ass test pilot, you come along at that stage and you go... like that, and stuff the stick forward. And the computer goes, oh dear, doesn't this idiot realise we're only 20 or 30 feet up, I'm going to creep down from here. So it completely de-skills the operation of the airplane, which is what we should do, because the people that are going to use the next generation of airplane, and this control system is going in the JSF, that's one of the things the Americans have taken from us. The people who are going to use the JSF in the future are using it to fight. They shouldn't have to use any of their sort of intellectual horsepower to learn how to fly it, only how to use it. Okay, this thing has been, as I said, been going on for some time now. It had got quite good by 1993. That was 10 years after I retired from full-time Harrier test flying. I had 19 years of the thing. And when I became 50, they said that was enough. So that's 10 years later. I went back to Bedford to fly that VARC aeroplane several times because the boffins wanted my views on the way the software was being developed. Because of course, although I've explained it in a very simple fashion, and it is that simple in principle. Getting the software to make the software fly the aeroplane nicely and beautifully and smoothly, and for the pilot easily to control how quickly it goes up and down and so on. That is quite an advanced job. And the last time I flew the aeroplane was in 1999. Now the chap in the front is a very important bloke, the safety pilot, Justin Paynes, squadron leader Justin Paynes. He was the second pilot to hover the JSF in the United States. A Royal Air Force squadron leader test pilot at Boscombe. And the first pilot, as we shall see in the movie in just a moment, was another Brit. So that's a measure of how deeply we are involved in the JSF program. But this software now, by 1999, it was brilliant. It was really magic. Okay, now what is this JSF? It's a stealthy supersonic to replace all of the world's F-16s, a short takeoff and vertical landing airplane to replace the world's Harriers, and a carrier vessel or naval airplane with a hook on it to replace the F-18As and Bs in Navy service. About 12 years ago now, 3 original JSF teams competed with paper designs. One team was led by Boeing, another one by Lockheed Martin, and the third by McDonnell Douglas. Only 2 of those teams were chosen to build and fly actual demonstrator airplanes, Boeing and Lockheed Martin. Now the engine, because this was a competition, had to be common, so they were both given the same engine, a bit like the way Vivo was using the Orpheus all those years ago. Okay, they both had to base their designs on a thing called a Pratt & Whitney F119, the engine of the day. Boeing's X-32B, as it was called, used Harrier pure jet lift principles. And this is the thing. So, here's the engine, and they added, because they were allowed to modify, the teams were allowed to modify the engine, but it had to start with the same basic engine. They added a couple of Harrier-like nozzles under the centre of gravity. Now, these nozzles were going to have hot air coming out of them. Other things that you would recognise are the sort of roll reaction controls. There's some stuff up the front here. What's this? Forward pitch nozzles. Okay, we understand forward reaction controls. Jet screen. Don't know what that is. Well, this air's hot. And so when it splashes down to the ground, some of it's going to go forward and rise and go in the intake. And that's bad news, because if you have warm air going into a jet engine intake, it doesn't do it any good at all. It loses a lot of thrust. And so they had cold air from the HP compressor before the fuel was burning, coming out of a sort of transverse slot to try and provide a screen to stop the hot air moving forward. It wasn't totally successful. This is what it looked like. I suppose somebody thought it was pretty. They shut the door off at the back with a big dang, you know, when they were forcing the air out of here. There's part of the engine before it was fitted. Not the prettiest thing. Okay, now let's quick look at the winner there. Martin's X-35B. They chose a totally different way of operating this thing. They were going to have a fan at the front and a swivelling nozzle at the back. So the whole front of the aeroplane is held up with this thing, and the back of the aeroplane is held up with that when you point it downwards. Now this thing is really nothing more nor less than a huge ventaxia. I mean huge. It's being driven by this shaft. So, if you like, this sort of bit like Vibo's idea. That shaft, folks, has got 26,000 shaft horsepower going down it. 26,000. 30 Formula One motor cars. And there's a nice little clutch and a gearbox that weigh nothing, you know. Some very advanced mechanical engineering has gone into this piece of kit, I tell you not. Very advanced indeed. This thing produces 16,000 pounds of thrust. When you drive the shaft and turn this thing, you naturally get less coming out the back, less jet exhaust coming out the back. In fact, they lose 6,000 pounds of thrust out the back. But they've gained 16 here. So if you like, there's an amplification factor over this system of 10,000 pounds. So this thing will hover with the same basic engine, 10,000 pounds heavier than the Boeing thing will. It's not magic, it's not something for nothing. It is that a high-speed jet is very less efficient as a propulsive device at slow speed than a propeller. It's no more complicated than that. Jet's extremely efficient as a propulsive device when you're going at high speed, but of course the hover is carried out at very low speed. Okay, that's what their lifting system looks like, and you notice it's got the roll controls. Right, it sits in there, we won't bother you with that, I mean you see. Now, they flew it. They flew it from the 23rd of June to the 6th of August. That's only 6 weeks. And in that time, they did everything that was necessary to demonstrate that they should win the competition. I mean, what an amazing achievement in 6 weeks. In 39 flights and 21.5 hours of flying out of Edwards, they were able to provide all the data that was necessary to win the competition. It was the only aeroplane that could do a short takeoff, level supersonic dash and a vertical landing in the same flight. And just to show that it wasn't difficult, they got a United States Marine Corps Major, Art Tomasetti, to have a crack at it. I shouldn't have said that, there's probably a Marine in the room, he'll be looking for me later. Right, they did 14 vertical short takeoffs, 17 vertical takeoffs, 6 short landings, 27 vertical landings. Routine, conversion and transition, what's that about? Well, the term transition is applied to when you transition from jet-borne flight to wing-borne flight. You go from one regime to the other. The Harrier transitions. It's an accelerating transition if you're going onto your wings. It's a decelerating transition if you're slowing down to the hover. And this thing does transitions. But the conversion bit is because it has to convert itself into a condition so that it can do a transition. Engage the fan, engage the clutch, spin the fan up, that sort of thing, turn the nozzle down at the back end and so on. So this all takes about 13 seconds on the downwind leg. Now, some of you may worry about that clutch. They've just demonstrated 1,500, because this is a research aeroplane and it's not flying anymore, and they are now designing the definitive one based on this principle that will go into service. This thing, this clutch has just been proven through 1,500 engagements. I said there was 26,000 shaft horsepower. Well, you don't engage the clutch, you know, when you're sucking that sort of horsepower up. The engine goes momentarily to idle, the clutch is engaged, and all it's doing is spinning up and overcoming the inertia of the vent axis, as it were. As soon as that bit of slip has happened and it's now driving it, 4 or 5 great bolts go through, good donk, and plungers go in. And so you've got a mechanical drive now through the clutch. It goes in hydraulically. Then the computer opens up the throttle, you know, and it's now got a perfectly good drive. So they have thought about this, and they flew the thing supersonically, which was necessary to win the competition as well. They refueled it, they did all these good things. And they did it under high temperature conditions. And the jet engine people in the room will know that doing everything at 2,500 feet above sea level and up to 94 degrees F makes life a lot harder, because all jet engines have less thrust under those circumstances. It says here that the next generation capability has a ground environment footprint equivalent to Harrier. What's that? Well, all this rubbish and boiling air underneath the aeroplane. How hot is it? How windy is it? How much damage can it do? It's similar to the Harrier. This really one picture to show why they won the competition. You see in the bottom right hand corner there, that's, let me just blow it up, that's an infrared film. So white is hot. I've had to draw the arrow on there because you can't see the stuff coming out of the fan, out the vent axis. But you can see this stuff coming out. And you can see how it's splashing forward. And can you see how the invisible cold air, which is splashing backwards as well as forward, has turned and taken complete control of the hot air? It has stopped this dreaded recirculation. And if you want my opinion, that one slide shows why they won the competition. They have a totally practical jet V-style aeroplane. And here's a little video of the aeroplane doing its first flights, its first hovers. A couple of years ago now. the pit. I think that the fact that they chose Simon says it all about. Here you see the aeroplane converting itself, opening the doors, turning the nozzle down. It says a lot that they chose a Brit to do this. There's Art Tomasetti walking about. Can't see anybody else in the way, so right. Let's see. Let's pull a stick back a bit and see if it'll go up. Well, it's got the nose wheel off nicely. How about the main wheel? Oh, well, just a little bit more. Now, I mean, is that thing under control, or is that thing under control? I mean, that's amazing, isn't it, for a first lift? If you had seen, I mean, I wouldn't show you the video of Bill trying to get that thing off the ground when it was tilted. I mean, this thing just shot about all over. I mean, it was a desperate exercise. And this is how good control engineers are now. I mean, Simon said afterwards that he felt he was almost a passenger. Well, he's not doing himself justice there, but it is nothing like as difficult a job. As the program manager, he's obviously quite pleased that it's worked. I've been banging on a bit, so I better just, I think we'll love you and leave you with that. The JSF is planned to be available from 2008. But until that golden day, folks, the best V-stop bomber in the world is the Harrier GR7, and this is the Harrier 2 family of aeroplane, the one that the Royal Air Force currently have at the moment. Lots of weapon stations, lots of weight carrying capability, very advanced, flying around at night, look out on, totally synthetic vision aids, you know, the thing they had in the Gulf. Excellent piece of kit. If you want the best V-stop fighter, then you need a Sea Harrier FA2 with its 4 AMRAAMs. But, and it's a very big but, folks, all of that, in my view, is only thanks to 4 British designers. Stanley Hooker and his boy Gordon Lewis, Sidney Cam and his boy Ralph Hooper. And I'm not sure that we grow blokes like that anymore, to be honest. It's not strictly fair on today's youngsters. The world today will not let individuals have the degree of responsibility and authority to make things happen anymore. It's got to be a committee, hasn't it, you know? Okay, thank you very much for your attention.
Yes, I just wondered, I know the last 4, just before we go on to questions, the last 4 slides with the 4 guys, that's what made it happen, but I think you can agree, we've got test pilots from a guy like John here, and his colleagues, they don't go without people like him. And I've been gobsmacked listening to it, because we've seen planes come and go, and we all think, as they are very great pieces of engineering, and for a chap like John who to show us it was relatively easy in layman's terms to understand. We've been overawed with it, but I'm sure you've got a few questions to put to John on his presentation, or maybe on what other things that John may have to say.
Yes, sir.
What happened to the French Balzac on this side?
Did you say what happened to the French Balzac?
Yeah.
Good question. What happened to the French Balzac? The French Balzac was a Mirage aeroplane, a large delta wing fighter, which had got 8 of the short SC-1s for vertically mounted engines. So it was a bigger and more grown-up piece of kit. It flew in the 60s. It had an ordinary horizontal engine, but it had 8 of these engines embedded. It crashed, basically. It crashed the first time with a lateral and directional problem during accelerating transition. The pilot was killed. The aeroplane was repairable. They repaired it, they flew it again, and in 1965, I was going to go out and fly it in about 2 weeks' time. I was on the 1127 then. But an American pilot was over in France flying it at that time, and he ran out of fuel in the hover. He ran the main tanks dry, so it fell on the ground and ended broadcast. So that was what happened to the Balzac. They also produced an airplane from that, which was called the Mirage 3V, which was an even bigger mother than the Balzac. And that had, again, 8 lifting engines, but they were bigger lifting engines, again Rolls-Royce. and again that one crashed again in transition. So they had their problems. I think they could have overcome their flying control problems with modern auto-stabilizers, flight control systems and the like, but essentially filling up the fuselage of a small military aeroplane with 8 engines, you know, uses up an awful lot of volume, awful lot of space, and where do you put the fuel, where do you put the equipment? I think that was the fallacy. And then you're going to carry these things around doing nothing for the rest of the flight until you start them up to land.
Do you think that, I mean, even an X-35 is very, very complicated mechanically?
Yeah.
And even the V-22 Osprey, again, is even more interesting.
Yeah.
But is it the Harrier concept is sort of like being superseded, or will it be gone back to, do you think?
No, the Harrier has come to the end of its time. The problem with the Harrier is that you can't make it go any faster. Going fast, folks, is not a matter of just having more thrust. It's the nature of the thrust. An engine for supersonic flight gets hold of a fairly small amount of air, takes it in through the intake, and pushes it out the back very fast. And of course, it's mass times velocity that matters. They take a very small mass and they give it a huge velocity, so that by the time you're going forwards very fast, you're still blowing out the back a lot faster than you're going forwards. A Harrier takes in an enormous M, a huge amount of air, and it blows it out the back relatively gently. So this means that by the time you got to about 0.9 or 0.95 of the speed of sound, you're not really blowing out the back any faster than you're going along. So it is a subsonic aeroplane, exactly the same as your airliners. I mean, some of the airliners that are flying around today have got twice the thrust of Concorde, but they're subsonic engines, and they're running out of puff, if you like, at high speed. And they're much more efficient, and they have other advantages. Well, that's the problem with the Harrier. Now, if you changed the Harrier engine to the supersonic sort, changed all the blading and the compressors and the turbine, and then had the air coming out that much faster, you can't, oh, and by the way, we only know how to make it go faster by making it go a lot hotter, or making it a lot hotter in the process. You can't have all this fire and heat right underneath the aeroplane, not in the centre of it. I mean, don't take my word for it that it's not hot underneath the Harrier. It stands there on rubber tyres. So it's a truly subsonic engine, and that is why we got away with the operating site flexibility. That's why we got away with the benign nature of what is happening underneath this thing. And they sorted it out with the X-35B and the Russians with the 141, by having the hot gas at the back. And the clever thing, where it's not going to do so much harm, and the clever thing is to have all this cold air up the front and controlling the hot gases. I think that's it. You can't, they want to fly supersonically, you see. Now, another problem with the Harrier concept, because you could say, well, throw away supersonics and just have subsonics. The hottest bit of the Harrier sits in the middle of its centre of gravity. And although the Harrier engine is not as hot as an ordinary supersonic airplane engine, it's still jolly hot at the back. And so all the heat-seeking missiles go straight into your centre of gravity. They don't knock a foot off the back end. They go thud right in the middle. And these two fundamental things you can't get away from. The Harrier's time is up, basically. I mean, I'm the last bloke to say it, but it is, you know.
But until the GFS is introduced.
Oh yes. I mean, I can't visualise the Harrier just being improved for another 50 years. The concept is fundamentally flawed if you want to take it any further than it's been taken already. Flawed with it won't go supersonic, and flawed that they have very clever heat-seeking missiles today that go thud into the middle of the airplane, and the middle of the airplane is only 3 feet behind you. You know, it's not the place to be hit. What's that?
Farley, I always understood Harriers were tiny and Harrier pilots had to be 5 foot 4 and that's tall. How does it work?
I was a lot taller to start with, but we all get shorter, don't we? Nothing to do with the Harrier. No, it's not that tiny. And in fact, the Harrier 2 has got a nice big cockpit on it, very big, deep, and yeah.
How tall are you?
I was 6'1.5" when I joined the Royal Air Force. I'm now 5'10". Yes, sir.
to get these things into the air, you've got all sorts of very complicated control systems, and then you make this transition into horizontal flight. And you've got to come back to the Earth again afterwards. What happens if all the clever control systems fail? Can you glide using your wings and make a sort of conventional dead stick landing?
No, no. Any more than if the clever control systems in the Airbus quit, the pilots can do anything about landing it. The pilots are not connected to the controls in an Airbus, or not the 320 series, 320, 330, 340. They're full fly-by-wire. They have a triplicated flight control system, made and designed by 3 different manufacturers, 3 different software houses. So there's no possible common fault. And these 3 vote. And if they don't like one of them, then it gets taken offline automatically. So, and I mean, Airbuses are just as reliable as any other airplane now. And that's the way that the military fly-by-wire is done as well. It's at least triple redundancy. And the final thing is that I became convinced about the superiority of automatics, and that's what these automatic flight control systems do. Back in 1965, when I was at Bedford, and I had this Bill of 27, but I had other jobs as well, and one of them was to help out the Blind Landing Experimental Unit. And I got airborne in a Comet 3 one day, and to look at the auto lands in this thing. In very strong crosswind. That was the whole object of the exercise. Could it cope with these very strong crosswinds? And you're sitting, this thing is crabbing in like this, and you're sitting out over the grass at the side of the runway, and the computer just swings the nose around and onto the centre line. And you're just sitting there as a safety pilot to bring the thing back if the automatics dump at any stage. And I said to the team in the back, I said, look, you know, if the system fails, I'm not landing here because I can't do that. I'm going to find a runway where it's a bit more into wind. So I came away from that flight, I mean, that's 40 years ago, convinced that automatics can fly aeroplanes much better than I can. So for me, there's no question, aeroplanes ought to be flown automatically. There is just actually one thing. Can they be made reliable enough? Not whether they should be automatic, but can they be made reliable enough? And they are getting the reliability up and up and up by various means. Yes, sir?
Is there any reason why you went from the ski jump again rather than catapult, the sea fight?
Oh yes, it's so simple. Oh, it's so simple. I mean, in fact, the Navy love it because there's extra storage space underneath the front of the ramp for the sailors to put kit in on the flight deck. And on any military ship, you're terribly short of space. There's nothing. There's no servicing. There's no maintenance. It's nothing. It's a completely trouble-free, easy way of getting airborne. It's amazingly good.
What is the difference between the Sea Harrier and a...
Yes, a good question. That first Sea Harrier, the sort of dodgy little bit of video I showed you at Farnborough in 1978, the difference is there between the RAF Harrier then and that new Sea Harrier was that we raised the cockpit 12 inches. We raised the sitting height 12 inches. We put a radar in the front. So that, but because the pilot was raised up, you could look back behind you, which you need to do in air combat in a fighter. The ordinary RAF Harrier at that time was for ground attack work. And the cockpit's down low, and if you look back, you looked into your intake. Well, that's no good for air combat. So that was the essential difference, that we raised the cockpit. We took out, Rolls-Royce took out magnesium, several magnesium alloy-based components from the engine, in particular the fan casing, because of the tremendous corrosion that you would have had in the salt environment. We put, we doubled the sensitivity of the roll controls. In other words, you had to move the stick only half as far with the Sea Harrier to get full control as you did with the RAF aeroplane. We put tight, so that you could chase a ship that's doing this, you know, more easily. And we did a tie-down job where we put hard points on the undercarriage and so on, so as they could chain the things to the deck. So the changes were negligible. I was very keen to have that the extra sensitivity, because I've been doing all the early ship flying with an RAF type of aeroplane, and it seemed to me that we could stand to have higher sensitivity. You didn't want to have to go 3 turns lock to lock. You know, it'd be nice if you could just do it, that sort of thing. And the aerodynamicist said, "Oh, you'll over control your, you know." Well, I knew we wouldn't, because I'd taken my hand in the hover and moved it halfway down the stick. Right? In fact, one day I got it so far down, the problem was whether or not I could stop the stick hitting the top of my western thing, you see. So I knew that by moving my hand right down, because I've now got a very sensitive stick, do you follow? And when I realised that made the thing nicer and better, I got the other guys to try it, and then we all just trooped off and stood there in a long line and said, "Change it, you know, before we fly," and it worked much better. Sorry, just one, yeah.
With the remote controls for slow flight and hovering,
Yes.
do they switch off?
Yes, good, very good question. These reaction controls, the pitch, roll and yaw. Yes, tapped off the engine, great big butterfly valve. So when the butterfly valve is across the top of the hole, no air. Like that, fine. Just like an ordinary throttle valve, butterfly valve. Don't leave the operation of that to the pilot, because he's going to forget one day. So when you raise the nozzles, the last bit, it goes from 18 to 0. There's a simple mechanical link which shuts the butterfly. And the first, you see, once you've got the nozzles less than 18, you don't need any reaction controls because you're going along pretty quick. Equally, when you start to put the nozzles down, the butterfly valve opens again. There was a castellated nut on the end of this shaft, and they didn't put the split pin in one day, and so the nozzle, the butterfly valve didn't open on a marine one day as he was turning downwind to come around and land on the ship. And of course, as he got slower, his ordinary controls didn't work as well, and he sussed that he had no reaction controls and accelerated away and diverted to land, and they found that the bolt had dropped out.
Is there any future for vertical take off transport aircraft?
No, none at all. I'm afraid you can't do it with that noise, you can't do it with that smell, you can't do it with that extra fuel consumption. And I mean, it would be nice to have a 747 that could just take off at Hyde Park Corner and just go halfway around the world. Well, people did dream of that, didn't they, once? But the lack of reality to this is that an airport is not just the runway. Where are you going to put all the people? Where are you going to put all the terminals? Where are you going to put all the bread vans? Where are you going to put all the customs? Where are you going to put all the, you know, an airport is a huge place, even without the runways. And so this city centre thing, I never have seen any sense in that. But I may be proved wrong one day.
Is it right there on more pilot accidents with Harriers than there were with conventional aircraft?
Yeah, another very good question. The Marine Corps broke an awful lot of aeroplanes at one stage. So many that they sent over one of their major generals to publicly stand up at the Royal United Services Institute in London and apologise that his blokes had made such a mess of the aeroplane. And this was about 1975 time. The first 3 years that they operated the aeroplane, 71 to 74, they had 0 accidents and 0 incidents. At that time, the Royal Air Force were losing 2 or 3 a year. And if you went and sat in an RAF crew room, the chaps there were shaking their heads and looking at each other saying, what are we doing wrong, you know? How can these stupid Marines be doing it so perfectly? Well, the first squadron was composed, nobody had less than 3 tours when he went on that first squadron. So they had all very senior, experienced guys. At the end of this, Marine Corps headquarters said, we told you, Harrier guys, that it wasn't necessary to have all that experience because you can see, you know, you haven't had any accidents. And so they just put anybody into the aeroplane then, without changing the training program. And the guys started going in like flies. In particular, they put helicopter pilots in. They said, well, helicopter pilots know how to hover. Of course they do. They enjoyed that. But they were creaming into the ground and hills and things at 400 and 500 knots because they weren't used to doing that. And now the Harrier, this accident rate thing, there's a yes and no to it. You have to decide what basis you're going to measure your accident by. Is it by tens of thousands of flying hours? Well, that's not very good in our case, because our missions are very close, short range often and so on, and close air support, and didn't it ought to be sorties? We do a lot of takeoffs and landings, and ordinary airplanes crash and they take off, you know. So when they looked at it, they reckoned that although the accident rate per so many thousand flying hours was worse, it wasn't that bad per sortie. And it was the nature of the very intensive, short-range, close to the ground sorties that they were doing that was pushing the rate up. You can have non-Harrier accidents in that military role. In other words, it isn't the machinery that's let you down. It's the operational role, which is very demanding. Short range, 4 or 5 sorties a day, you know, this sort of thing.
Why was it so successful in the Falklands as a fighter?
Why was it? Because the Argentinians used the wrong strategy. We had 20 Sea Harriers down there, 20 Harriers to start with, not all Sea Harriers. The Argentinians had nearly 130 aeroplanes, quite a lot of them supersonic. They were very brave guys and very skillful guys, but they were working to the wrong brief. Their brief was, ignore the Harriers, attack the ships. And so they were pressing on with their attacks, covered in bombs and weapons and so on, and not being able to manoeuvre much. I won't say they were sitting ducks, but they were relatively easy to shoot down. If the Argentinian Air Force had briefed their pilots, when you see a Harrier, throw your bombs away and fight it. At the end of the first week, we would have had none left. I mean, you can't deal with a 7-to-1, you know, outnumbering, and they would have got rid of all the Harriers, and they could then have attacked the ships in peace and quiet, as it were. But no, they were very brave. They were going to attack the ships, and I mean, yes, the Harriers is quite a good aeroplane when it comes to doing interceptions, and the Sidewinder in his day was quite a good missile. But the tactics didn't help the Argentinians. Really didn't. Yes.
Vectors must have no use in situations like that.
Yeah, oh yes, I know what you're talking about. Vectoring and forward flight. This is using the nozzle lever in air combat. Yes. Harry Blott, who was probably the foremost Marine Corps Harrier pilot, he always used to say that you should never get shot down in a Harrier by anything that you have seen, whether it be an aeroplane or a missile. Because at the last moment, if you are skillful enough, you can throw the engine into reverse thrust, and you can change your speed so quickly that you can force the missile or the aeroplane to overshoot, destroy the aiming solution of the opposition. But of course you do have to see them. I mean, all the good guys who've been in the recent programme on the television from the Battle of Britain, I mean, all these guys admitted that quite a lot of chaps were shot down by somebody they never saw, never knew was there at all.
Just a question going on.
Mm-hmm.
This new one, is it GSM?
Yes.
Now, it's looking like it's a big stick to just achieve speed. I picked up something that was at a transition stage or something, it takes 15 seconds. So basically, it appears that in just this need for speed and the American way, you've lost your delicacy. Is that
Well,
right?
I think that's a slight oversimplification. Yes, they do want it to go faster, but they wanted to do lots of other things, and one of the things is be very stealthy, and it is very stealthy. Now, stealthy doesn't mean you're invisible on radar, it just means you're a lot harder to find on radar than normal. It doesn't mean that you have no heat signature, it means you've got a lot less. It doesn't mean, well, it does mean in the case of the GSF that you have no smoke trail from your engine. I mean, so it is a smallish aeroplane, and so you reduce the visual signature. You're trying to get all the signatures of the aeroplane right down. So that this, and I honestly believe it'll be the last aeroplane ever used in manned combat, the GSF. I shan't be around for you to shake my hand when that gets proven, but I hope one, perhaps. But I mean, all the other roles, other than close air support, in support of our troops, will be carried out by unmanned and missiles, unmanned combat vehicles and missiles. But when it comes to helping our own troops at a range of 40 or 50 miles and backing them up with this powerful close air support, then you want your airplane to be stealthy so as you don't get shot down quite as often, and you've got to have a bloke in it, because he's got to work with the troops on the ground very closely and so on. At least that's the stage of play at the moment. Now, the United States Air Force, which wasn't going to have any JSFs, and in fact I ought to change my slide, they have decided now that they are going to have a percentage. They're only working on what the percentage is. The percentage of their buy will be the vertical version, because they have tweaked what I've just said. And that is that if they don't have a few vertical aeroplanes, they will have no aeroplanes left with pilots in combat in 30 years' time.
Right, ladies and gentlemen, that was a very interesting question that John's answered. I'd like to ask Jeff to offer our vote of thanks to John for such a very good question.
Okay, thank you, Ian. On behalf of everybody, may I say, well, what can one say? Here we have a man who spent the whole of his working career as a test pilot, is that probably correct? Still here to tell the tale. He's been dependent upon a whole host of great engineers, as we've heard the story, and he's told us an enormous story very graphically, and very entertaining and enthusiastic way. I thank you very much indeed. Can I ask everybody who joins institutions, there are 5 institutions, sections here, so thank you.